Thank you, Akshay. So I'm going to talk about quantifying Eisenstein congruence. By quantifying just means counting. So rather than start by explaining what that is, I'm going to try to motivate why we want to do that. So this story has a long history. So it starts maybe with Kummer in the maybe 1850s. So Kummer was studying Fermat's last theorem. So he wanted to show, so Fermat, so he wanted to show that there's no solutions to in integers to an equation like this. No solutions. So one way to try to attack this problem is to factor the equation like this. So x to the p equals z to the p minus y, and then you can factor this as z minus zeta p to the I, y, where I equals 0 to p minus 1, whereas zeta p is a piece root of unity. So this is in the ring, zeta p. So what you realize quickly is that since this side is like is a piece power, and this is a product of things that don't look like piece powers, you could try to derive a contradiction from this. But that only works, so you can derive a contradiction. If this ring ZP works like usual integers. And Kummer determined what exactly works like means. Specifically, if the ideal class group which we denote by class group of Q zeta p has no p torsion. So this is some group that measures, it's a finite abelian group that measures how far this ring is from being a unique factorization domain. So you may hope that, okay, maybe this group never has p torsion, and then we can solve Fermat's last theorem. But that's not correct, because Fermat's last theorem was not proven for another 100-something years. So what Kummer proved is that Kummer's theorem is that this class group has p torsion if and only if p divides zeta of 1 minus k for some even k between 0 and p, something like that. So for example, so here zeta means the Riemann zeta function. So it's sort of strange to say that, if you're not used to it, to say that a number divides the value of some analytic function. But these numbers are actually rational numbers. And here this p divides means p divides the numerator of that rational number. So for example, zeta of 1 minus 12 is 691 divided by 32,760. And 691 is a prime number. It doesn't divide the bottom. So class group of Q adjoint zeta 691 has 691 torsion. Okay. And in fact, using this theorem, Kummer proved that there are there are infinitely many prime numbers p for which this condition holds, and therefore for this condition holds. So, so except for those infinitely many, he can prove for Maslo's theorem. Okay. So, so the next people in our story are Ribbit, Maser, Wiles. So they were trying to answer the following question, which is if p does divide this zeta of 1 minus k, how can I to produce a class in this p torsion class. So p torsion, something that's killed by p. So meaning, how do I make this more explicit? So Kummer's proof was more like by looking at the numbers and comparing these two numbers, but not really like taking p, dividing that number, and producing some class. So the new idea by Ribbit and Maser and Wiles is to use modular forms. So modular forms. So this same number, zeta of 1 minus k, appears in the theory of modular forms in the simplest example of a modular form, which is the Eisenstein series. So Eisenstein series is the easiest, the first example you learn of a modular form, and they can be labeled by numbers, k, and the constant term is zeta of 1 minus k. So that means that if p divides zeta of 1 minus k, then what you can prove is there's a congruence. So there's a different modular form f congruent to f, this thing mod p, where this guy, where f is a cusp form. So Eisenstein series are like the easy modular forms, and cusp forms are like the hard modular forms. So because p divides this thing, you get a congruence between the difficult modular form and the easy modular form. And from the existence of this f, you can explicitly produce some class. So from f, you can build a class in this Q zeta p torsion thing. Okay, so right, and so you can refine this kind of thing in many ways, like Ribbit and Maser and Wiles did. But I want to talk about a different kind of refinement than what they were doing. So now we're getting closer to the present day. So the next people are Sharifi, Fukaya, and Kato around the 2010s. So that includes present day. So we have this sort of picture. We have class groups here. And we have zeta values here. Here, we have modular forms here. And these things are all related to each other. So there's sort of a triangle of things being related to each other. And I suppose the idea of Ribbit and Mazur and Wiles is that they're really interested in connecting these two sides of the triangle, and they use this other part as an intermediary to try to attack this arrow. So you go from zeta to modular forms to class groups, and that shows these two things are related. But in fact, the philosophy of these people is that these arrows are these are forgetful arrows. And that this arrow is more of a correspondence. Meaning these two things contain the same amount of information, but this thing forgets some information. So for example, the zeta value can tell you the order of the class group. But not the abelian group structure, the group structure. So if I have a finite abelian group, the order of the group is an important invariant, but not a complete invariant. You can have two non-isomorphic groups that have the same. So these zeta values are just numbers, and so they can tell you how big the group is, but they can't tell you the exact group structure. And that can be important because you may want to know, for example, I think if you want to prove the Fermat's last theorem, if you knew that a number of generators that you needed for the class group was small enough, you can still make that proof work. So number of generators is something that the order doesn't know. So Sharifi made the following conjecture, which I will just state vaguely. So he on one side you have this class group, and now here I'm going to write the P infinity. So that just means take only the part of this finite abelian group where that is killed by some power of P. And then on this side you have these Eisenstein congruences. This F that is congruent to the E by P up to some equivalence. And Sharifi produces maps in both directions between these two spaces as abelian groups. So not just bijections, but they have the same. These are group homomorphisms. And the conjecture is that these two maps are inverse to each other. So in particular, both of these maps are isomorphisms, and their composition is the identity. So, and this is important because, well, I'm not going to explain what they are, but this map is something very explicit. So meaning you can take something, some modular form, which is some kind of something living in the world of functions, of complex numbers and so on, and use it to produce something purely mysterious and arithmetic in some very explicit manner. So that's a very unusual kind of conjecture. So okay, so let me state one theorem of me and my collaborator Carl Wong Eriksson is that under some mild assumption at least this upsilon map is an isomorphism. So we know that in some way there's some inverse to this map. So the group structure of this is controlled by the group structure of this, but we don't know that the inverse is this explicit thing. And the general, I have to end now, but the general theme of my work, or what I want to study this year, is around these kind of ideas that so the theme at the is that counting the dimension or other parts of the structure of Eisenstein congruences and this should be related to some deep arithmetic of number fields. Okay, so